All right. Any questions from last class? We basically review some linear algebra, a lot of linear algebra, I would say. It was like a 1 year course condensed in 1 hour or so, 1 hour and 8 minutes actually. Any questions about that? No, good. Just to let you know that the assignment was posted, and of course, as it couldn't be any other way, it's about linear algebra. So you have that nice symmetric 10 by 10 matrix there. So the problem asks you to compute the eigenvalues of the matrix, first using one of the libraries that we're going to be discussing today, and then the second part to compare those with the power method that we discussed last class. Okay? And the power method you will have to implement from scratch. Of course, you can also use linear algebra routines for doing whatever you had to do in the power method. And then the last part is to use something that is quite neat, I would say, which is the Gershgorin theorem. How many of you have heard about the Gershgorin theorem? Oh, yeah, let me ask them.
Is it circles or is it a second line?
This is.
On the line, or would they be?
Oh, okay. Excellent question. So now I can talk about the Gershgorin theorem. So the theorem applies for any kind of matrices. And we were discussing, and in this case, with a real matrix. But the theorem applies also for complex matrices. So when you compute the eigenvalues of a complex matrix, your values are on a plane, in the complex plane. But when the matrix is real and when the eigenvalues are real, your circles reduce to intervals, only on the real axis. So if you have an eigenvalue, let's say 1i, or i1, being I the imaginary unit, it will lay in that plane, right? And the circle will be something that is the addition of the theorem works for columns or rows, so it will be the addition of all the remaining elements in the row or the column. That's the radius of the circle. Now, if your matrix is real, like in this case, and symmetric even more, your eigenvalues will be all real, and they will be only the real. So this is the real axis, imaginary axis. So in this case, these are intervals. Okay, so the theorem is general enough that applies for complex eigenvalues. So that's why it says circles on the plane, but in this particular case are intervals on the real axis. Okay, if you want to draw the intervals or the circles in the complex plane, you're welcome to do it. Okay. So I just wanted to mention this, and I think it's due on March 1st, so not next Wednesday because it's reading week, but Wednesday after that. Okay? Any questions about this? Any other questions about this? Was this clear? Yeah? All right. So let's take a look then at the utilities part of the linear algebra. So last class we reviewed a bit of theory. Today we're going to be talking about the packages that you can use for actually do some numerical linear algebra. In particular, we're going to focus in two, BLAS and LAPACK. We're going to talk a bit more about other ones, but these ones are quite neat and useful. So we mentioned this also last class. There are many techniques and many methods that you can implement for dealing with linear algebra, either by for solving the linear systems, for computing eigenvalues, for doing matrix decomposition, different kind of things, right? The thing is, these techniques have been in place for a long time, and the libraries that we are going to see today, they have been developed for a long time. So many of them have been optimized until the last line of code. Every line of code has been thought for people or by people that actually deals with that all day, and is their profession basically to deal with that. So our suggestion is, whenever there is a library there that has been tested, that has been proven to be optimized until the end, just try to use it. Okay, you may have to spend some time learning. You will see. I know we will sugarcoat this for you. Some of the routines are kind of cryptic, and you need to get used to the terminology and the nomenclature, basically. But it's worth to learn that and use these tools that have been optimized until the last line of code. Okay, which packages are available there? So one of the, actually this is kind of a repository issue with, or an interface, is the netlib that contains information for BLAS and LAPACK. Mostly this is written in Fortran 77, which is quite old, as you can notice, but they have interfaces for C or C++. Most of these codes are public domain or freely licensed, so you are free to use it. It's maintained by University of Tennessee, I think, and Oak Ridge National Labs. The other one, Etsy, is also maintained by one of the national labs. This happens a lot. Like, I don't know what is the deal with the national labs in the States, but they like to compete each other. They have a visualization package called one visit and the other Paraview. Each of them is maintained by one of the national labs, and their goal is to basically do the same. So I think it's some kind of friendly family competition going on there. This may be kind of the same. The only difference is that Etsy is, well, it's open source as well, but it's C++ directly, and can deal with partial differential equations and iterative linear solvers. Okay, so somehow they are complementary in this case, not necessarily competing with each other. There are other ones. Another one by another national lab, Trilinos, is a collection of 50 plus packages, maybe more now, which include linear solvers and preconditioners. Remember, we talked about the conditioning number last time, and the whole field of preconditioning research. So these guys can do that for you. Okay, and for sure there are many others. If you look, there are parallel versions of, for instance, LAPACK. It's called LAPACK. One interesting thing, though, is that even when this library has been developed and optimized, especially the parallel versions, to get you the best performance, I don't remember the name. Remember when we went to the Computer Ontario Research Day 2 years ago, there was someone presenting a shift in the paradigm that people is trying to use to solve these linear algebra operations. And the bottom line is that nowadays, computing on the node is cheaper than sending information on the net, or passing information to your next node. So many operations now, or the approach is to switch, instead of sending information out of the node, recompute things on the node. So some of these libraries have, or are being rethinked in terms of that. Anyway, so let's take a look at BLAS. So BLAS stands for Basic Linear Algebra Subroutines. It's a standard that has been for a while. It's highly tuned for different platforms. You may be familiar with some of them. By the way, if you are interested in using GPUs, NVIDIA has a nice implementation called QBLAS, which is CUDA BLAS. There's a difference between the interface and the implementation, and this is something that we are going to see more in detail in a second. It includes higher order operations like matrix factorizations and Gaussian elimination. Those are defined in LAPACK and on top of BLAS. So let's take a look. So this categorization, and this is where things start to get a bit more cryptic in terms of names and how to call the routines. There are basically three families or three levels of different routines, and you will see something similar with LAPACK. So the first level are, and each level is like gaining in complexity in the sense of which operations you can achieve or which structures you deal with. The first level implies dealing with dot products, like for instance S dot is the single dot product. SASP is solving the linear system AX plus Y. Okay, so SASP, the set stands for double complex. So we are going to see prefixes in front of the names where S is single, D is double, C stands for complex, and Z is a double complex matrix. So S is a single variable with a dot product between two vectors. SASP in that case is a double complex matrix solving this linear system AX plus 1. The level 2 type of operations or routines are matrix vector multiplications. So initially you have vectors, basically level 1. Level 2 is matrix vector, and here D stands for double again. CE in this case is now a general matrix. So remember we spent a good amount of time last class discussing that the structure of the matrices. Different kind of matrices like upper triangular, lower triangular, banded matrices, diagonal. So these routines or these libraries knows about all these type of matrices and can take advantage of that structure. So it's always a good idea, if you know the type of matrix that you are dealing with, to use the appropriate routine for dealing with that specific matrix. So the types that we may have are general, where there is no specific structure underlying, Hermitian, symmetric, triangular, triangular banded, triangular packet, Hermitian banded, and general banded. So now you can specify the type of, so you specify the type of variable that you have, and then the type of matrix that you have, and finally the operation. So in this case, it's always matrix vector multiplication, so that's the MV, matrix vector multiplication. So here we have a double general matrix vector multiplication, double symmetric matrix vector multiplication. Okay. The final level, level 3, stands for matrix-matrix operations. Okay, so we start with a scalar vector, vector matrix, and matrix-matrix. That's the level 3. So, and again, the nomenclature is kind of the same. So you have a single general matrix-matrix multiplication or a complex triangular matrix-matrix multiplication. Okay, so those prefixes of those names are going to specify the routine, but also have information about the type or the structure of the matrix that we want to use. Okay. As I say, these are somehow cryptic names. You get used after a while, but it's good to know, and it's good to try to remember, or at least look at the names and the type of matrix that you are dealing with in order to know which is the best routine to apply for each case. Okay. Okay, so this is a kind of teaser slide, but why bothering using these libraries? I think I mentioned this at the beginning, but if you think about this, in the worst case, you will end up doing this kind of operations, right? 3 nested for loops, where basically all what you want to do is compute your final result, like a matrix-matrix multiplication in that case, right? If you prefer, instead of doing that, implementing your own codes, your own routines, basically the opposite will be, okay, if I had the libraries, I had to find the libraries, download, install the libraries, sometimes it implies compiling, most of the times, figure out how to link with the libraries. Most of these libraries, I told you, or at least BLAS is Fortran, so there are C Fortran issues that we're going to see in the examples. So the question is, why just not write it and use our own routines? In addition to the argument that I told you about the debugging that they have been out for a while now, is the fact that the performance that you're going to get in your best implementation, or the best implementation that you can achieve with a triple loop kind of matrix multiplication, doesn't compare with the best vector and parallel code that you may achieve. So this is a factor of what? 5 at least. And this is performance, like giga float operation points per second. And this is just a matrix multiplication. So this is a 2-core experiment. I think it's quite old, so this means these numbers may have changed. So the triple loop, which was what we were seeing before here, this kind of implementation, gives you this number of operations per second. You can easily achieve factor of 2 if you use vector instructions. We haven't talked much about vector instructions, have we? I don't think so. So vector instruction is something quite interesting, and it's something that is is available to use in modern chips, in modern CPUs, and is that if you have a vector, the compiler can figure out, okay, this is a vector, and it can have to do operations like adding two vectors. It can add all of them together at the same time. So some of these libraries may take that into account. So then you can have multi-threads, like using more than one core per node. Like in the case of SciNet, you have been using SciNet, you know that there are 8 cores in each node, so you can have multi-threads. Or you can have even the best implementation, vector and parallel codes working together. And you can see that the performance is quite remarkable. So implementing, closing this gap between the vector and parallel code and the triple loop that one can naively try to implement is not easy to achieve. And some of these libraries, especially the parallel versions of these libraries, do a great job getting the best performance that you can achieve, on top of being prune of bugs and have been tested for a while. Okay, so I hope that this kind of convinces you why going through the pain of learning the cryptic names and using those libraries instead of implementing your own. Okay, any questions?
Matrix size, is it going to be an n by n or just n?
What do you mean n by, so?
Like
In this case?
Yeah.
Yes, in this case it may be, I don't know if we have information about that in the plot, but take the simplest case as a n square matrix. Yeah, and dense, and yeah, on top of that you can have routines like saying, okay, if it is a banded matrix, that's make things even better, right? Because I know about the structure and I can take advantage of that. I didn't talk much, but there is also, I don't think there is information here, but there is also memory issues, right? And we're going to see, we have been discussing since the PDE class that some matrices may have this special structure like banded matrices, right? And if I'm dealing with a stencil that has, I don't know, 10,000 by 10,000, I don't need to store 10,000 square elements for that matrix. I can just store the diagonal upper and lower diagonals, right? But I can take advantage of that at the moment of implementing my multiplication routines, right? And BLAS knows about that. Okay. Yep, sorry. The y-axis is basically the performance of the routine. So the largest is better performance. You get more floating point operations per second. Like think about throw issues. Okay. Any other questions? Okay. So let's go back to BLAS and LAPACK. So these are references are provided by the NetLib implementation. I think I have a link at the beginning. The thing is that many vendors or commercial software provide their own versions, specialized for their own hardware. For instance, like Intel has MKL, so it's as good or in some cases even better than these ones. AMD provides ACML, and then IBM has ESSL. Open source variants of those are ACLAS, GoToBLAS, and OpenBLAS. OpenBLAS is quite neat because it's pretty easy to install and follow. So I had an example using actually OpenBLAS, I think. As I said, there are many Fortran functions, but there are also C interfaces using CBLAS and LAPACK. So I have an example to show the difference when you are calling one of the Fortran functions, or the Fortran calls, and the C call. And the main difference is how the different languages deal with passing arrays or not. That's the main difference. So how to install BLAS, how to use BLAS. So let's say this first part, if you want to install in your own computer, this is one of the easiest libraries to install. So basically you can clone this GitHub repository for OpenBLAS. Okay, just clone that repository, go to the OpenBLAS directory, choose, you will have to have a Fortran compiler. As I told you, these are Fortran routines, so you will have to have a Fortran compiler like GFortran, for instance. do a make for preparing the installation, like it's going to compile the routines when you do make, and by setting fc equals shift_fortran, basically you are telling the make file to set the variable of the Fortran compiler to shift_fortran. If you have another Fortran compiler, choose your favorite one. If you leave it without specifying, I think it will try to figure out which Fortran compiler is installed in your system. And then for installing, just to make install and set the prefix to wherever you want to install. For instance, your home directory, and then open BLAS, wherever you want to. Okay. Just remember that you will need to know where the installation is going to happen, where you want to install the libraries. Okay. For linking, so this is the installation part. First part is just installation. The second part is a suggestion how to make the header and library directories available for you always when you want to compile your codes. So in this case, one suggestion is go to your bashrc file that is loaded every time that you open a session in your terminal, and add these lines. So export BLAS inc, that's the header directory, and then wherever you put it, it will be an include directory with the header functions, as we define when Rancis discusses modularity. And then there is another directory, lib, where the actual libraries are going to be. So that's, you can name it BLAS lib. Those are suggested names. You can use the names that you want. And finally, because these are libraries that are dynamically linked when you compile, set the LD library path to whatever was before plus the new directory where you installed the libraries of OpenBLAS. Okay. Yep. Here, whatever was before in your system. So if you have other libraries that you have installed before, LD library path will have that for sure. If it is empty, it's empty, and this may be the first one. By the end of the course, you probably will have this. You will have NetCDF, GSL, another one I'm forgetting. I don't know, whatever you want to start. So the LD library path is a variable that usually exists in any kind of Unix, Linux environment, and is where the compilers are going to try to go and look for libraries that are dynamically linked with your compilation. Okay, we're going to see an example of how to compile this and what flags we have to use to specify using the BLAS.
So we can library and edit our path.
Yeah, to the library path. Not the usual path, because the path is used to find executables or binaries, right? That's the main difference. So this is kind of a path for binaries, but only for libraries, not for binaries. Alternatively, you can use the ones that we have already installed on Signet. So if you have a Signet account, most of you already have a Signet account already, you can just go to one of the GPC development nodes, find the OpenBLAS modules that we have. I don't know if this is the last one, remember? Maybe. Try module find OpenBLAS, and it will throw all the versions that that we have. And then load the version that you prefer to use. And that will basically load this path for you on Signet, with the special nomenclature that we use, something like OpenBLAS Signet Inc. or OpenBLAS Signet Lib. Okay. Any questions about this? The installation should go pretty smooth. It's not one of these libraries that give you headaches when you install it. Even on Mac OS, I think it works just fine. Okay. So let's take a look at one simple example. So we're going to start easy. So this is just a scalar vector multiplication. And one of the things that you will see is that these routines try to recycle a lot. They are kind of eco-friendly, too eco-friendly if you ask. What I mean with that is that if you have a vector x and you want to multiply or scale the vector, that's how they call it, scale the vector by a coefficient, it's going to store the result in the same vector that you use. Okay, so let's take a look at the code. So we are doing including the usual library iostream, and now we are going, this is the new library cBLAS, the header file, the arguments as usual. So here we have a vector 1, 2, 3, the coefficient that we want to use for multiply. This guy I will explain in a second. So basically, this routine allows you to do the multiplication and take like strides. So if I want to multiply only the first, third, and fifth element of the vector, I can say 2. So it will jump. So it's a stride in the elements of the vector. So in this case, I want to multiply all the elements, so I just put 1 there. You need to specify the size of the vector, and 3. And in this case, I'm having just a direct Fortran call. So it's dscal, so it's a double type of vector. It's a scalar or scaling the vector or a scalar multiplication of the vector. And you notice that the Fortran call has an underscore. The other thing that you will notice is I'm passing the content of the variables. And this is because the way that Fortran passes the variables. Okay? It's different than from C that pass by reference in the case of Fortran pass by value. Okay? Now, because we want the result, and I told you the result is stored in the vector itself, we had to pass by value, but the first element, so we will know where to put the data back. So that's why we're doing this. Basically, this for loop is just for printing the result. But before showing how it looks, what it prints out, let me show you the C version. So in this case, we're using the C BLAS implementation or interface. So in this case, you need to add the C BLAS underscore thing before the name of the function. It's the same function dscal, but in this case, it's C BLAS. And you can notice you don't need to pass anything by value itself. You just go as the pointer in C. And the rest of the code is exactly the same. Okay? Any questions about this?
Why is argc and argv, why are they there? Not used, sir.
They are not being used, but if you wish, it's good practice in case that your code, but you can leave it void if you want. Yeah. Okay. Similar with the return zero, we talked about that before. How to compile? Okay, let's say that we want to compile on your local machine. Remember, we put the values of the installation path in this variable BLAS inc and BLAS lib. And basically, I'm using the C++ compiler. The name of the code is dscal_ccc. Want to generate the file called dscal. I had to include, remember, this minus capital I is where the header files of the functions I want to use are. So in this case, are the header files of the C BLAS implementation, so or the Fortran implementation, but whatever those are in the BLAS inc directory that we defined before. I need to include also where the library files are. That's we do with minus capital L. And finally, we need a flag for saying that we want to use the Open BLAS library. So this is the last flag, this tiny L Open BLAS here.
After the capital I.
Yeah, you do minus I, whatever header file, minus I, whatever header file. Okay. If you are using Signet, this is the nomenclature I was mentioning. You will notice all the modules have this nomenclature, Signet underscore, the name of the module underscore inc, and the same for the library, Signet underscore, the name of the module Open BLAS, in this case, underscore lib. Okay, so that is the advantage of doing things on Signet. You don't need to install anything, just load the appropriate module, and then use those generic variables. Yep.
When you say compiling on Signet, do you mean like when, for example, in the future we're going to use the Signet?
Or now. I know that some of you, at least one of you, was using Signet for solving the modularization assignment, I think. Okay. So you are welcome to try and use Signet from now on, if you want.
I have no idea.
Unless that we ask you to install a particular library in one assignment, but I don't think that's the case. Even RRA is installed on Signet. So yeah, if you feel like, okay, I want to compile things on Signet, don't screw my machine or whatever, you can do it. Just use the libraries that we have installed on Signet. Okay. You won't see, let me see, so far until next week, the next one, or 2 weeks from now, probably you won't see any difference in the codes. They are not too compute intense. But yeah, you can try and use Signet right now. Actually, it's a good practice because we will know if your accounts are working or not. I think all of them will be working, because if you can log in with your signed credentials into the education website, it should be working. But it's not a bad idea to start trying.
Explain this, however, in the course, because I actually have no idea how you actually use
Okay.
SignNet now.
So my first suggestion is we have on March 8th an intro to SignNet, and we may have a mini intro to SignNet in one of these lectures. But yeah, so if you don't know how to, just use your computer. It's just in case that I know some of you may be using, and also it's a good idea just to mention that these things are available on SignNet. Okay? So this is compilation. We have just one module or one file, so we don't need to worry much about linking with other modules. But remember, you will need to include these guys, the header and the library path, in order to the compiler for finding the appropriate routines that you want to use in the implementation. How to run it? Pretty easy. Just the name of the thing and it runs. And basically, because I was printing the elements of the array, it's just printing the scaled version. So that number 4323 multiplied by each of those numbers, and that is what is printing out. Okay, so it looks like a lot of trouble, like remembering compilation flags, remembering the cryptic names of the routines, just for doing a multiplication of elements. But things are going to scale up to be more interesting and more complicated, and this is how we start. Okay, any questions? Okay. So I told you many of these things are kind of cryptic, at least in the name part. Places where you can find a lot of help in particular is the netlib reference guide, if you wish. And also, the funny thing or the nice thing that happens with these libraries is when you install it, it also installs in a man file for you. So man files are help files that you can use with the man command, which stands for manual. So if I don't exactly know how to use the double general matrix multiplication, that's DGE-MM, I can do just man DGE-MM, wherever the library is installed. And then it will pop up a help page saying, okay, this performs one of the matrix operations. And basically, the way to say is, when you do one matrix operation, always think that these things do more than one thing. So it can also do the matrix A multiplied by the matrix B, but also multiplied by a coefficient and adding a third matrix multiplied by another term. So that is the matrix version. It tells you basically what type has to be each of the parameters that you are going to use in the function. And it also tells you a bit of the help, a bit of what these things are. So in this case, operator X and operator X prime, and the matrices A and B, and the dimensions. And this page continues. So there are several lines of help there. Okay?
C++ itself doesn't take care of parallelization.
No.
If you have to do a loop, and the language itself doesn't.
Yes, so far we haven't done anything at all related to parallelization, and these versions, the versions that we're discussing today, BLAS, C-BLAS, LAPACK, or LAPACK, don't do parallelization for you. There are parallel versions. LAPACK is the one for LAPACK, I think, if I remember properly.
Depends what kind of parallelization. Like credit, so on and no.
Yeah.
Part of AL as well as class.
Right.
So just using the course on no.
Will you multi-thread? Yeah.
Not the reference one, but Open BLAS or ML. For you, if you just take the library version as parallel.
But if we take the default one, same speed as our loop.
No.
No.
It'll still be about 20 times faster.
Yeah.
Because it doesn't do, because it has cleverer things to initialize.
Yeah.
Even singles.
Yeah, it doesn't do that simple and naive approach of the three nested loops. It does something, I don't even know what it does, but that's something better.
It's an advanced class.
Yeah, that we had to take.
You don't have to take. The library is there.
Yeah, exactly. All right. What else? Oh, yes. So we're going to start to see something funny. So as you can see, so this is a matrix multiplication. And you see at the arguments, there are like how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like more than 10 arguments there. So I told you, it's actually doing just not matrix multiplication. It has the possibility of computing a scalar in front of the matrix multiplication, adding another term. But it also has the chance of specifying something underlying the structure of the matrix. And these things are these LDA, LDB, and LDC indicators, which stands for leading dimension of the matrix A, matrix B, and matrix C. So what we mean with that is you can actually take a matrix and for whatever reason want to multiply subblocks of the matrices and not the whole matrix per se. If you want kind of an artificial example of how this works, think about this canonical Jordan decomposition that we taught last class, where the matrix not necessarily has to be diagonalized, but it can be diagonalized by blocks depending on the nature of the matrix. The point being is you can specify the blocks that you want to take in the matrix to do the operation alone and not the whole matrix. And how you do that, you do with this leading dimension of the matrix. So logically, your matrix, or you might think of your matrix like this rectangular thing. We talk about how we store the things on memory. Physically, it's an allocation of consecutive spaces in memory, hopefully. And this, let's say that you want to just consider the subblock in the matrix. So we have the element 3, 2, and 4, 2, because this is row major store, will be consecutive the first element in the row and then the second, and then will come, because it's stored, then you have a gap until the next part of the block, okay, which it will be the element 4, 3, 3, and 4, 3, right? Those are the next one. Now, if I want to do that, if I want to consider these two blocks, I had to specify which is the leading dimension, which is the jump that I have to have there in order to reach the next one. Okay? Usually you won't do that, but this is a feature that the routine has for you. Okay? In general, you put just that equal to the dimension of the matrix, like an m by m matrix, and you are done. But in case that you may consider, you may want to specify something else there. Okay? In addition to that, the BLAS also allow you to store things at your own way, like having row major or column major implementations of the matrix, how you lay down the matrix in memory. Okay? So let's take a look at how we actually implement this. And the other thing is, I told you this at the beginning, all these recycled things keep coming along. So if I want to if I want to actually perform the whole operation of alpha times A times B plus beta times C, all is going to be stored in C. If you don't have a third matrix, that is where actually your result of the matrix multiplication going to be. Okay. So again, this is an example of the double general matrix multiplication. We use BLAS. So in this case, we will have MKN phi, which are the dimensions of the matrix, are going to be M by M, K by K, and M by N. Because we just want to multiply the matrices, alpha is 1, so the factor in front of the A-B multiplication is just 1, and beta is 0. So there is no extra term. That's basically what we are saying. We are allocating dynamically space for A, B, and C. So that is how we actually deal with two-dimensional arrays, or in this case, matrices. And then we basically just put some values there. So for C, we don't care. It's just field of zeros. A and B has some given values depending on the value of the index that we use to cover. Okay. And the call to the library, it goes like this. So it's the BLAS, so it's the C implementation. It's the double general matrix multiplication. We are specifying that we are using row major implementation for putting the data in memory. These are for specifying. You can say, okay, this is the transpose of the matrix or not. So if you don't, basically you don't need to transpose. You have the matrix. So in this case, these are not transposed. These are the dimensions of the matrices, M and K. The coefficient alpha, which in this case I say is 1. The matrix A, the leading dimension of the matrix, because we want the whole matrix is the same as the dimension of the matrix. The matrix B, the leading dimension of the matrix B, again, because we want the whole matrix is the dimension of the matrix. Beta, which is 0, so even if you don't want to do the addition with the third matrix, you need to specify that parameter and see where it's going to store the result of the matrix multiplication. Okay, these dots are just printing out the matrix. Any questions about this? Yep, sure. So in this case is row major, the representation I'm doing in the memory laydown. But you can specify row major or column major. So it's up to you how you lay down the implementation, the representation of the matrix in the algorithm. You first, yes.
No, so yes, row major means by row.
Oh yes, I was saying row major, right? Like,
Yeah, so
the row is column major. Sorry.
So the picture is called, and the reason that it is column major here, because this is talking versus BLAS. All of this was originally Fortran.
Yeah.
Column. Ever do mixed language? Row,
Yeah.
like Fortran, and you have matrices in both. Stick with C. You're probably just going to do row major. C. If you C BLAS as fast as C BLAS here, but there are packages like Eigen library or matrices. You can actually pick the way you want. Pick one way, and then will use C BLAS. So picture is column major, default mode, and if you row major, plus. But if you really like to code everything,
Is it so if you
yes, that's right.
Okay. But, yep. It's a way just to fill some values in the matrix. You choose whichever value. Just choose like something. Like yep.
so indirect,
If you're working in Fortran,
if I'm working in C,
In C.
I'm calling Fortran function.
oh no, now you have to worry about all of it. Because basically everything that you think is one matrix is
It's the transpose.
as the transpose. Because you have to, well, or you pass the transpose flag.
Oh,
Yeah.
Okay, so, but you have to think about switching back and forth all the time.
Yeah.
But it gets tricky.
we're using C function, I'm calling.
Right. So that's why these guys specifically
Don't
ask
run.
you for the major or for how it's stored, because they know that at the end of the day, this C BLAS _ dgem is calling the Fortran. By giving these flags, it'll just make sure that it'll.
So this is how it looks the output. So that's the original matrix, and these are the numbers that come from this I plus 1 and minus I minus 1, and the matrix multiplication. Okay. So that's how you do matrix multiplication. So let's take a look at LAPACK. So let's see how to actually. So LAPACK is the linear algebra package. So it contains this variety of solvers for linear systems. So let's take a look how to do that. It can do also. It actually was something that is going to do while solving the linear system is going to solve doing these LU decompositions that we discussed last class and creating this pivoting matrix for reaching the lower upper triangular matrix decomposition. Basically, the nomenclature is the same as in BLAS. So after you get used to the nomenclature of the single, double, general, something, triangular, something, is kind of all the routines start with the same thing. There are actually 3 categories as well, like auxiliary, computational, and driver routines. So we're going to see those. And the C interface is with LAPACK E. So there's some links there. The things that it can perform in terms of factorization is LU decomposition, lower triangulars, transpose decomposition. For Hermitians, you're dealing with complex matrices. It can do this orthogonal decomposition that we discussed last time with the orthogonal matrix and the upper triangular chunk, basically. Similarly, for for Hermitian matrices. It can deal with symmetric or Hermitian or non-symmetric eigenvalue decompositions. This is quite neat, something that you were probably going to need. It can compute singular value decompositions and eigenvalue and singular value. Can that repeated? Yeah, singular value decompositions. Again, if you install LAPACK, you will have the man pages of the routines, so you can just do man. And in this case, we are looking at a double general solver for the linear system AX equal B. So one of the nice things that these routines will allow you is, because the way it works, it basically created a composition for the matrix A of the system, then you can specify as many vectors P you want. So basically, it will allow you to solve at once many systems with AX equal different B's. Okay, so we're going to see actually examples with a couple of B's. Here is telling you how is doing the decomposition. So A is going to be decomposed in this pivoting matrices, which is nothing else than this change of basis matrices, such that at the end you get an L and a U decomposition. Okay. So let's take a look. Also, you can do with subblock of the matrices. So you have again the LDA and LDB, so leading dimensions for the matrices, pivoting indices, and rank high size. So RHS specify how many rank high size you have, how many vectors B you are specifying. So let's take a look at how to use it. So in this case, we're going to include the LAPACK E header files. We will have two rank high size vectors B. So we're going to be solving actually AX equal B1, B2, if you wish. The leading dimension I specify at the very beginning because we want to deal with the whole matrix equal to the dimension of the matrix. And in this case, it's a 3 by 3 matrix. We are going to use this index pivoting vector with the dimensions equal, the same number of dimensions as the matrix. And the new thing is that we will have an info flag. So this is an integer that basically allows you to collect the result, the status of the reporting the result of the operation of solving the system. Initialization of the matrix A. Basically, leading dimension times n is a generalization for saying n squared, and you basically fill all the values of A. And here similarly for B. So in this case, we have B. Yeah, okay. So the leading dimension of B is the dimension of B, and then two rank high size. So the first vector and the second vector for B. Okay. And then the way to call the LAPACK E DCESP function is you assign whatever the function came back in the info flag. Again, we're specifying to use the column measure and the number of right-hand sides, the matrix, the dimension of the matrix, this index or vector of pivoting that is going to be filled, and then the matrix B and the leading dimension of B. Okay, so if we file this, now the flags, we're still using the BLAS implementation. That's right, yeah. And then what returns is, and here is, well, it's not printed, but whatever is returned in the vector X. So you get these two vectors that solve the system, and then it provides you also details of the factorization of the matrix and the pivoting indices. So this IPEV vector is filled with the number of the permutations that you had to do in the rows for getting this factorization. No, this one is included, right, in the BLAS, I think.
LAPACK open BLAS is to get both BLAS and so strictly accept libraries, but open BLAS is fine. So if you just have open BLAS, get another BLAS and select.
Okay. So what about these structured matrices, like the banded matrices, or matrices that are non-dense? So the types that are associated with that, or the types that we can use, are banded matrices, like if you have like just in the diagonals and sub-diagonals. This one is very frequent and very useful because it's 3 diagonals, so that one already knows that you have the diagonal, upper and lower sub-diagonals. And then we may have symmetric positive definite matrices, as we saw in last class. So how we deal with those? So let's take an example again, solving a linear system, but in this case with the previous matrix, where it's similar to the one that we saw for the PDEs, but now it has some force, probably higher order decomposition. So it has 1, 4, 4. So notice that, okay, we're going to use again LAPACK. We're going to use a 5 by 5 dimensions in this case. And again, we're going to be solving for 2 vectors. So the number of rank size is 2. This is a nice way of setting the leading dimension, so you don't need to worry too much. You always put equal to the dimension of the matrix. You are dealing with the whole matrix, and that is it. So again, we need the info flag for knowing the status of the solution. We define the lower diagonal with 1 less element. The diagonal has 5 elements as the dimension of the matrix, and the upper diagonal as well has 1 less element. Okay. The vectors are actually 3, not 2. So this is a typo here. So we have 3 independent vectors. Okay. So whatever those are. And again, the only thing that we need to specify now instead of the DGE is this is a triangular, double general, triangular symmetric matrix. Sorry, banded matrix. Yeah. So again, column major, number of dimensions, rank high psi, and now the difference that we specify the 3 diagonals: lower diagonal, diagonal, and upper diagonal. The vector of independent terms and the leading dimension of the independent vectors. Yep. Sorry, second. Oh, well, it will be nice to have it then dynamically allocated. It's just a matter of choice. It doesn't matter in the communication with the routine. But yeah, initially I was lazy here. Okay. And so the compilation goes as before. And when you run now, you get 3 solutions for X because we have 3 independent vectors. Okay. What about sparse matrices? We talked a bit about them. The truth is that there is no official implementation of sparse matrices. There is a sparse BLAS or a nice sparse BLAS. I think the matrix template library may have something, but there are no standards as there are for the other for more general matrices. Okay, but there are some references there if you want to take a look. What else? So these are some useful references. Again, if you want to deal in particular, well, if you are using something from MKL, this is a very interesting link for taking a look. But then these other ones are just for the standard implementations of LAPACK and BLAS. And well, I think the conclusions is like the same as we have been mentioning and hammering you guys. Try to use these libraries, try to get familiar with them. Try to exploit the structure of your matrices. In the problem, I think we have a finished positive symmetric matrix. So whatever implementation you use, try to use that's underlying the routines that you are going to use. Yeah, choose your functions accordingly to the structure of the matrix that you have. Okay. I think this is it for today. Any questions?
Maybe good to mention is that all these examples, all the matrices, for some reason we're all one.
Yep. Yeah. Yeah.
So that is odd, right? And it's very on C or even on C++. How are these matrices or just vectors? So because you specify what leading is, in other words, where the next row starts, these routines know that this is a matrix every time you pass n elements. The routines, LAPACK and BLAS, only care about the fact that these are now contiguous in memory or skipped by the lead. So they can get a linear array. When you're using any other package than linear arrays, so for instance, dimensional arrays in C or plus eigen R array, you have to make sure that those matrices have contiguous elements. In other words, that if row 1 is in here, row 2 isn't somewhere that it is. So we've seen in the array like that even just using C++, there's two ways to allocate. And one where you allocate rows one at a time, and one where you whole block. The latter one, memory layout. First one, which is the standard one, you'll find text not preferred. LAPACK. Get it C++ text. This is how you create dimensional array. That dimensional array will not. So this has a warning, and that's why all these examples are just using a flat layout of the matrix.
And how does R?
Array by sign and everything.
Taking dimension is
Well, it depends how it's laid out. In Fortran, it's columns. And
okay. Yeah.
so yeah, it's an odd concept, but it makes it it makes submatrices possible. If you don't have submatrices, LDA is going to be your column.
Okay.
This is a bit of like a general question, because I've done a bit of that stuff in Python, and I know that Python at the end of the day is also using LAPACK and stuff. But it's much simpler, however, to code it.
Right.
So I was just going to ask, like, is there an actual advantage, like doing things in C++ in terms, I don't know, maybe I'm missing the point in some specific aspect, just because everything is using LAPACK. So.
But in terms of Python, you mean? Compare C++ with Python?
can you cite //
Well, I mean,
Well-
something like when you're using, so let's say NumPy, as far as I know, it's really doing everything, either like C or.
Yeah.
Right, but
but
there's
there's still
yes, that's true once you're at the LAPACK level. But everything else you do, like filling matrix, in your data, feeding the file, still done by Python. Python is still going to have to look at your script line by line.
Yeah.
Has to figure out for every variable what its type is. Has to basically distinguish which type it is, which LAPACK routine call. And so there's overhead.
there's still a lot of overhead. So we're
So if the majority of your stuff is spent in a LAPACK or BLAS call, correct, then it doesn't matter. Right. And you might as well. But if there's a good bit of other stuff going on, then we'll see you. The other thing that's harder to do, I guess, is parallelization.
there are also things that the compiler can do for you, right? This thing of having defined the variables at the very beginning, specifying the types, not only makes the compilation faster, but also allows the compiler to reshuffle and reorder things, especially if you are using a level of optimization 3, which is quite aggressive, so it can reorder instructions just to make it run faster.
Come back to the Python suggestion. If you just take your Python code as is and you run it through Python, it's not going to be any faster than Python. But with the extensions for Python or Python show it what it should be doing in C, then yes, you can. So you're still going halfway.
Yeah.
Sometimes it's a good way, but if you know you're going to be performance sensitive ahead of time, you might as well.
Well, that is really open.
Oh, that would be nice. Not getting the update that we hope, but sure. Right. Oh, yeah.
What is the computational cost to pass the matrix?
Yeah, excellent question. So that can be substantial. If it's a small matrix, might not be much, but if you're looking at 10,000 by 10,000, you're moving a lot of bytes. Although it's in memory, you're still moving them around. And so it's better to pass the flag saying, I want to